how can we write the logarithm function as a power series? We have written the exponential, the sine, and the cosine as power series, so logarithm seems like the next natural candidate. Well, right off the bat, things are going to be a little bit different. The domain of the function ln is only positive reals. It's not all the reals like it was for exponential, sine, or cosine. So, for example, I cannot expect to write it as a power series centered at 0. The function is not even defined at 0. It has a vertical asymptote. And whatever I manage to do, the interval of convergence of this power series will have to be finite. There are two options. There are two things I can try to do. I either try to write this Taylor series centered at some positive number, not at 0, or instead I can shift the function, and instead of looking at ln x, I look at ln of 1 plus x, and then I can try to write the Taylor series centered at 0, the Maclaurin series. These two things are pretty much the same calculation. It's just that the shift is done at different stages. There is something psychological that makes us believe that power series centered at 0 are easier, perhaps simply because we are more used to thinking of those, so I'm going to go with option 2. I want to write this function, logarithm of 1 plus x, as a power series centered at 0. I want to try to relate this function to any of the other ones that I have already written as a power series, but unfortunately, logarithm seems too different from all of them. Luckily, the derivative of this function is easier. The derivative of this function is 1 over 1 plus x, and now this one looks very similar to the geometric series, which is already written as a power series. Let's remember what the geometric series is. And this will do, because I can transform this derivative into something like the geometric series, then write the derivative as a power series, and then integrate it to get the original function as a power series. And that's exactly what I'm going to do. I need to write it as 1 over 1 minus the variable, so I'm going to multiply it by minus 1 twice. And I'll write it as 1 over 1 minus x. And now I can use this equation using minus x instead of x. That's my power series. I'm going to separate the minus 1 to make it easier to integrate things. There. So that's the derivative, f prime. But if the derivative is a power series, I know the original function is also a power series, and I can integrate it the same way I integrate a polynomial, term by term. An antiderivative of x to the n is x to the n plus 1 over n plus 1, and don't forget the integration constant. I'll find out what the integration constant is in a moment, but first, where will all of this be true? Well, the original expansion was when the absolute value of x is less than 1, so this one will be when the absolute value of minus x is less than 1, but that's the same thing as the absolute value of x. And when I take a derivative or an antiderivative of a power series term by term, then the radius of convergence doesn't change. So this is still going to be true when the absolute value of x is less than 1. The behavior at the endpoints of the interval of convergence may change when taking a derivative or an antiderivative. So it is possible that this new expansion happens to also be true at 1 or minus 1. I don't know that yet. But what I know is that for sure will be true when the absolute value of x is smaller than 1. Now, how do I find out the value of c? The best way is to evaluate at some easy point. And the easiest number to evaluate this power series is when x equals 0. When I do that, I get that f of 0 is equal to this power series at 0 is simply 0. Notice that the smallest exponent is 1 plus c. And f of 0 is logarithm of 1, which happens to be 0. Okay, so the constant was 0 after all. So this is the formula I have proven. Logarithm of 1 plus x equals to this power series. Perhaps it feels a bit unsatisfying that the exponent of x is not exactly the index of the sum. If so, we can fix this easily. I can do a change of index, and what I was calling n plus 1, I'm going to call it m. And then, since n goes from 0 to infinity, m will go from 1 to infinity, and then I change the index everywhere else. And that's exactly the same power series, but perhaps this is a more standard way to write it. Or if you prefer to remember the first few terms of the series, they are this. And finally, very important, remember that this expansion for the logarithm is only true when the absolute value of x is smaller than 1. To conclude, as an exercise, I invite you to try to write the arctangent function as a power series centered at 0. It is a very, very similar derivation to the one I have done in this video for the logarithm.